the person who took more advantage in the world about this microscope and is the right person to show how all the possibilities that this microscope offer. So thank you, Suman, and I pass the word to you.
Thanks. Can you see my screen and hear me properly?
Perfect.
All right. So yeah, this is, of course, is going to be more of an application talk, and I'm going to talk about some of the stuff that I did, along with some of the stuff that Lionel did, and but the common theme is, of course, the use of the DIVER detector. And I'm going to, I didn't look at it, but I'm going to guess you already have been told how the DIVER detector works, but I'll just go very briefly and then move on to the actual applications. So the DIVER detector, and this is the picture that is assembled in Georgetown, not the one from LFD, but it's basically the part which is right here. So it's a conventional 2-photon upright microscope, which is from Olympus, which is shown here, and the DIVER detector is here. The DIVER detector is a trans, it's in the forward direction, the imaging is done. And basically there's a refractive index matching between the sample, the detector assembly, and the PMT, which stops the loss of light due to reflections. And this is sort of a blown up version of it. So inside this, you have multiple filters that you can use a stepper motor to move into, and that lets us image the different things. These are all glass filters, and now there are 2 filters which can let us do multispectral imaging using sine and cosine filter, similar to what Nick talked yesterday. And so when you excite the sample in a conventional microscope, the objective itself collects the detection, but in DIVER, the wide area photocathode, which is 1 inch by 1 inch, so it's a much larger area that collects the light. And as you go deeper and deeper, this angle actually increases, which gives the DIVER is increased sensitivity at a deeper level compared to a normal microscope. There's also an effect from 2-photon, which has been explained by Chris Chu before, where the normal microscope looks less just below the surface. So this gives the DIVER a very high ability to look deeper into the tissue. And the refractive index mismatch is a very simple idea that you can see if you put a bunch of glass slides and look through the image, some writing here, you see a very faint, but if you put just water in the image, which is not a perfect refractive index along to glass, but it's a better mismatch from 1.1 to 1.52. And here is 1.33 to 1.52, and you see it much brighter. So that's the basic idea of and due to this loss of reflection. And the other important part is because you do not have a lot of optics here, light, especially in the lower wavelength range, UV and close to a very low visible, which in a normal microscope, by going through the different optics, gets lost. You don't lose that. What that means we can use the full fold of a laser and do second and third harmonic imaging with a normal, here it's inside, but even a titanium sapphire microscope. Because if you do third harmonic imaging with a titanium sapphire at 1050, the wavelength that you will see the light is at 350, which is very difficult to see in a normal microscope. So you get up to 10,000, up to 1,000 times signal gain based on the situation. Now, the difference is, so what I'm going to talk about, a part of that talk is going to focus on harmonic generation microscopy. So I just wanted to introduce that. So in fluorescence, you excite the molecule. So this is 2-photon excitation. It goes to excited state, comes back, and the emission happens basically all angles around that point of excitation. So you can pick up from any angle. However, in second harmonic generation, what happens? We basically send an oscillating field, but because of the breakdown of the center of symmetry of the molecule, for example, collagen and myosin in the tissue, the electronic oscillation here goes equal height in both direction as you are putting a field. However, it goes, there is a resultant field because this is an harmonic potential. And that gives rise to the second harmonic. Now in second harmonic, the most of the light goes in the forward direction, and only a very part of the light gets reflected back to the direction of the excitation, and that's the normal conventional microscope way. Again, it goes into a state which is not exactly a proper excitation state, and because it's a virtual state, there is no delay associated with it. So in fluorescence, you go to the excited state, you relax and then come back, that gives you this lifetime of fluorescence. However, in second harmonic, because it's a state which is virtual, there is no delay and you get a lifetime of 0. Now, in terms of excitation, you can excite anywhere from 700 to 800 nanometer, let's say, and you get a signal which is second harmonic at 350 nanometer if you excite it around here. And you get the fluorescence signal which is normally coming from tissue around 400 nanometer upwards. By doing that, you can separate the second harmonic very easily from the fluorescence signal of the system, while doing the same excitation at 700 to 740 nanometer for both. So you can use one-shot excitation. Now, this is just to show how the second harmonic images look like. This is fluorescence, this is in kidney. So this is basically looking at collagen 1 and fibrosis, and I'll come back to it in a second. Now, as I mentioned, the diver is in the forward detection, and as you can imagine that you'll see much more second harmonic signal in the forward detection. So by looking at the diver detector, which gives with its high sensitivity, originally, although it was developed for deep tissue imaging, we figured that it would be really good for imaging harmonic generation, and that's sort of what we did. The other important part, again, as I mentioned, this is actually excited state, but this is a virtual state. So the diver, the signal of SHG from the diver will resemble the laser pulse. However, there will be a delay in the fluorescence signal. What it means in terms of phasor is your fluorescence signal would be somewhere in the middle, but your second harmonic signal would be basically at this position, which is lifetime of 0. And that gives you another separation from separating out bleed-through fluorescence or anything else that might combine the complicate the second harmonic generation when excited at 700 to 750 nanometer wavelength. Now, the first thing we use this is we use it to separate collagen types, originally based on flame. So these are just intensity images of collagen gels that was formed in the from solution in collagen 1 through 5. And when we actually used the phasor lifetime to see if they have different lifetime, they seem to have different lifetime, especially collagen 1 and collagen 3. There's a large separation, and these two are important because they are involved in different types of fibrosis. Collagen and 4 and 5, they don't really form fiber-like structure, that's why you don't see them. Now, when you take the second harmonic imaging, you can do basically the same area. So you can do second harmonic imaging. So this is the intensity. However, we can use now this phasor to see, okay, if it's actually second harmonic or is something else. So it turns out that collagen 3, the signal is mostly coming from fluorescence and not second harmonic, although mostly because this is so bright compared to the other collagens that is bleeding through the collagen second harmonic signal when excited at 750. We use this even in combination of where we mixed collagen 1 and 3. So this is at high fluorescence range, which is the lifetime of collagen 3, you can select out collagen 3, and low fluorescence intensity range, you can select out collagen 1, and you can see the second harmonic is all collagen 1 and non-collagen 3. Now, we use this idea to look at mouse femurs. So this is a whole bone section of a mouse femur. Now, one of the things with the diver is it lets you image really large areas. So I think right now it lets you image up to 1.2 millimeter and 1.2 millimeter. That's the field of view, which is pretty unheard of in normal microscope. So by doing that, we can stick the autofluorescence on second harmonic image, and we can use um, their lifetime behavior to show that where the collagen 1 goes, where mostly collagen 3 rich areas goes. Now, of course, there is a overlap here between the NADH, which makes this analysis slightly more difficult than if it was just collagen, right? But we could figure out a way on a particular type of mice, which is called smart MRI data. It's a mice that develops bone myelofibrosis, and we could see the extent of the myelofibrosis by basically using a color coding between collagen 1 and collagen 3 to see how collagen 3 increases in the internal part of this bone on this smart MRI device. So that was my first work with the DIVER imaging system, and that was published in 2015. Now, one of the other main projects we looked at is quantification of the UUO mice model using Freeman SAG. So let me explain the model first. So what you do is you tie up one of the kidneys, and as the blood flow is restricted, it basically becomes fibrotic over time. So you take, once this is done at different time points, you sacrifice the mice, and you look at, you slice the kidney, and you look at the amount of fiber generation over time. And again, we are using green color here to separate out the second harmonic, and red color to separate out the autofluorescence that is bleeding through to the second harmonic channel. And if you look at 7 days between the control and the disease mice, you see there's a large difference already started to show up in the fibrosis or collagen 1 accumulation, especially around the glomerular space, which is important for this sort of kidney fibrosis models, right? And then at 14 days, it becomes worse compared to the control. And at 21 days, it goes really, really bad. And then we can quantify this. We can quantify basically how many pixels are covered by the green compared to how many pixels covered by the autofluorescence. And we can see that ratio actually increasing with time. Now, one thing to be noted here is the right kidney, which is actually is not getting, is normal, that's also getting worse because it's doing 2 kidneys work by itself, and that hasn't been really shown in conventional stuff before, but we could see that. Now, another important part is like we can look at each individual sample. So there are 6 samples originally in each, with 10 images in each, and each case with the days of UVO, you see this ratio going up in every single area of these mice. Now, this y-axis is different for different ones. So, of course, the time with time, this is a much higher, is 5, and with 7 days is only at 0.4. But we can see that, we can quantify that. And we can, of course, because DIVER is a 3D imaging system, we can look at it, we can look at how these fibers are oriented in the 3D. Now, one other important part of using this sort of idea is this. This is both 7 day, same areas. This is, so this is all 7 day. Same areas imaged both times. This is with normally how people do it with background correction. If you do background correction, you're also going to lose fibers which are not exactly oriented along the path that you are exciting. And that's why you see a much less signal difference between these two. So we couldn't differentiate originally, but these samples are done without any background correction. And by doing that, because you're not getting rid of any signal, we actually get a much better separation between the disease and non-disease states. So other examples, and so this is basically Lionel and Sasha's paper, Enrico. So they have looked at mouse brain, which has been labeled with YFP. They can go up really deep, and these are mouse brains which are non-clear, I believe. So, most of the time you see these images, they're in clear tissue, but this is in a non-clear tissue. They looked at high-fat mouse liver in 3D. Again, they can look at and separate different things. Again, this is an eye of a mouse embryo, and if you can you can select different lifetimes, different components, and I believe so this shows up how different components are oriented in a mouse eye. Then again, in the other part of the paper, Lionel's, because he is the guy who does all the lung stuff, they have looked into rat lung to see the separation again in there. And these are again large area images, which is not very difficult to do. And you can see the difference between two different types of lung. And if you have questions about it, I'll just refer to Lionel about that. The other examples, of course, is third harmonic generation, which, so I didn't go into the detail of it, but third harmonic generation is basically the way you compare. So third harmonic generation happens at the edge of a diffractive index mismatch. So if you have two separate diffractive indexes which are very different, it will be a high mismatch and it will give a really high third harmonic generation separation. To do that, you excite at 1050 and we look at 350 nanometer, same as SHG window, but the excitation is different. And by doing that, you can see this is the fluorescence image and this is the third harmonic image. And you can see in adipose tissue, you can see the tissue boundaries very well in third harmonic image. Fat droplets, which are big and have a very different refractive index than the rest of the image, that can be easily seen. So this is here what is seen here. So these are low fat and high fat diet. And in high fat diet, you can see the fat droplet and the age of the fat droplet being really bright. You can also look at things in the cells. I believe these are again droplets, and in the nerve, and in bacteria, because again, you can do basically image of the bacteria, non-labeled image of the bacteria using the third harmonic generation. With the sine cosine filter that has been explained before, you can again use the sine cosine filter. And these are the same bone samples I originally showed. So this is different, again, lifetime separation. And this is the lifetime phasor image. But as you can see, with the spectral phasor that is collected with sine cosine filters approach, you can separate out the collagen 1 and collagen 3 areas exactly how you would separate out in lifetime. So in this case, they are complementary, but you can imagine by combining these things together, you get much better separation between things which has either overlapping spectral information or overlapping lifetime information. So you'll be able to split them out into more. Now, another thing that we used in, and this is slightly changing the time, slightly changing the field, is human kidney biopsies. And this has renal parenchymal injuries. So they basically, from patients of diabetic nephropathy, and they're looking at what's the injury associated with it. So when we originally started, we basically took the images, and these are different extent of image. So this has no disease, it's normal. And then you have mild, moderate, and severe diseases, and these are core biopsies, right? And if you look at the phasor plot, you see that with higher disease, the phasor goes to higher phase angle. So the lifetime is actually increasing as the extent of disease is progressing. Now, we wanted to quantify that, and the first thing we did is the original, how phasor has been analyzed for a long time, is by splitting this histogram into two and seeing what fraction of one compared to the other. And as you can see, the MCD has mostly purple, and this one is mostly yellow, the severe one. And of course, we can do at different areas, different parts of the images. By looking at that, we could potentially calculate just by this fraction similar to the second harmonic analysis I did before. Doing that, we can separate out the MCD from the other disease states, but we could not separate out individual disease states very well. And the reason is very simple. There is a lot more variability in this system. So if you are averaging everything out and giving it one number, you are not going to be able to get the heterogeneity in the system to look at. And so these are just phasor plots. You can see the phasor plots moving. So we went back to something that I did with Indico some time ago about, which is called multiparametric phasor approach. So this is an approach which is based on machine learning towards phasor analysis, and is oriented towards separating stages of disease based on receiver operating characteristics curves and how we can separate them. So, and it's based on a method called distance method, which is originally developed by Indico quite a few years ago before this. So the way it works is you have your phasor plot, but this is a heat map. And you can think of this as a 3D plot where the y-axis is basically the number, the z-axis is number of phasor points. The way we did it, we split it into 4 separate segments. And in each segment, we calculate a few different parameters. We calculated the center position of that particular segment, which is GNS, the length and the width of this that is fitted into this. And then you also can calculate the number of molecules and the angle it is creating with this 0, 0 in the center. Now, so from each of them, you get 6 parameters, so 24 parameters if you split into 2. And those 24 parameters can allow us to separate between the samples. One of the ways to think about it, let's say you have only a few pixels, which is up here. So if you do average, you might not catch it. But if you split it into 4 at the lower intensity level, or lower number of phasor points level, they will be actually important. So that's what gives it the sensitivity. So based on that, we calculate the average spectrum for the 2 separate groups. One is for the control and one is for the disease state. And just by putting this weight associated with each of those 24 parameters, and once we have that average spectrum, we select out how each of these spectrum is differentiated, and we calculate the maximum separation between the 2 groups, which is again the control and the most disease. And once the separations are done and we know these values of WI, we can actually use that to create the separation index. So this separation index would define how a particular image goes into the disease state or in a non-disease state. So in terms of actual imaging, this is how it looks. So if they're very well separated, the 2 groups, they would be at -10 to +10. That's the number here. If they're not that well separated, it will be somewhere in the middle. But once the separation is achieved, you can use a unknown sample, which you don't know what the extent of the disease is, and you can select out where this appears. So this case, this is more towards control, this is more in middle, this is more towards the disease. But it can also happen that some areas of it are actually in the control, some areas of it in the disease, and this will let us separate each individual image compared to the whole sample by itself. So we did that. So we looked at the mild to separate. So we used MCD and severe to separate them out. And then we looked at mild and moderate. So this is all results together, and we start seeing the shift towards more and more disease states as disease is progressing. And this is just to show that we get a really good separation between the two types of state. And this is individual images. Again, in this case, you see some of the areas are on this side, some of the areas on the other side, but which is even more evident here. But in some cases, they are only disease, so only mostly disease. So we did this for mild, we can do this for moderate, we can do it for individual images. And by doing that, we can separate out which of the areas where it is that the disease is shown up. And that's sort of got published this year. And that's pretty much all I wanted to show, just some examples of the DIVER detector and how things work. And finally, of course, the